Hi, this is an example problem. Calculate the electric potential due to multiple point charges. Pause for a moment and read the question. So we are going to look and see how more than one point charges can contribute to the electric potential in the space around them. In this problem, we're going to look at one particular point, point P, and we're going to calculate the electric potential due to charges Q2 and Q3 at point P. This may remind you a little bit about the calculation of the electric field at point B due to 2-point charges. And this would be something like you'd have to include the contributions from charge 2 at point P and add that to the contribution from charge 3 at point P. Now the big difference here is that the electric field is a vector, and so this thing here is a vector addition equation. Whereas electric potential, that has to do with energy. Remember, joules per coulomb, that's the units of electric potential. Energy is a scalar, and so this is just simple algebraic addition. So this is a lot easier than doing the electric field stuff, or maybe not easier, just a lot less time consuming. All right, so let's go ahead and do part A. Again, I'm going to need to use the equation for calculating electric potential due to a point charge, which is V is equal to KQ divided by R. And notice that this V could be positive or negative depending on the sign of the charge Q. You need to put the sign in there. So in this case, let's go ahead and calculate first the electric potential at point P due to charge 2. In that case, I'm going to look at charge 2, there it is, and the distance between charge 2 and the point P is given 0.15 meters, that's R there. Sometimes we write this as RP2, and we know the value of K, 9 times 10 to the 9th newtons, meters squared per coulomb squared. Q, minus 6 microcoulombs, and the distance 0.15 meters. Put that in the calculator, we get an answer minus 3.6 times 10 to the 5th joules per coulomb. Now let's repeat the calculation for the electric potential at point P due to charge Q3. I should put a 2 here. And then the distance from P to 3. We can use some of this information over again, I think. In this case, charge Q3 is minus 5 microcoulombs. So let's put a minus 5 there. And the distance is, it's the same distance. It's also 0.15 meters. Picture doesn't quite look like it, but we're going to go with that, 0.15 meters. And when we put this into the calculator, we get a value of minus 3.0 times 10 to the 5th joules per coulomb. Now finally, to go ahead and get the electric potential at point P due to both charges, we just need to go ahead and add the individual contributions from each point charge. So here's the first one. Plus, here's the second one. And when we add those together, we get an answer equal to minus 6.6 times 10 to the 5th joules per coulomb. All right, let's look at part B. And there's an image that goes with that too. So we just did part A. Let's go ahead and take a look at part B. We've got these two fixed source charges here. Now we're going to go look at a third charge, Q1. It's not a source of the potential, but it's going to experience the potential, and it's going to obtain a potential energy due to its interaction with the other two charges that have created the potential at that location P. let's go ahead and calculate this. So for part B, calculate the potential energy of Q1 if it is placed at point P due to its interaction with Q2 and Q3. Well, that's pretty straightforward. We're just going to use this equation that relates potential energy when we place a charge, Q1, at a location in space where there's an electric potential due to other source charges. So the potential energy in this case for Q1 at that position, it's going to be multiply the charge Q1 4 microcoulombs times the electric potential at that position. And we're going to see that again, the coulombs cancel out nicely. That electric potential turns into a potential energy of that charge, and we plug those numbers in, we get a value minus 2.64 joules. Now, as we've seen before, potential energy can be negative or positive. It doesn't matter. What really is important with potential energy is not the sign, but the change from one value to another at some other location. So for example, we're at minus 2.64 joules here. If there's a position in space that has even lower, say minus 5 joules or something, where this charge could move to spontaneously to decrease its potential energy, it could speed up, gain kinetic in doing that. On the other hand, if I wanted to move it somewhere to a higher value of potential energy, it's not going to go there by itself. You're going to have to force it there. You have to push it along, do work to get it to move to a location with higher potential energy. It's the same idea as if you want to go climb a mountain. You're not naturally going to go up that mountain unless you put the work to push yourself up against the force of gravity. And when you do that, you get to a higher height, which means you have a greater gravitational potential energy. Same idea here with electricity and the electrical force.